Assalamu alaikum. Stability of linear systems is determined by the poles of the system. Poles are the roots of this denominator polynomial. If any of the poles has positive real part, then the response of the system will be unbounded, that for a bounded input. That is, the system is unstable. If the order of this denominator polynomial is less, for example 2 or 3, then we can easily determine the roots of this denominator polynomial. However, if the degree of this denominator polynomial becomes large, then finding the roots of this denominator by analytical approach by hand becomes quite tedious. Routh's stability criterion helps us to determine the stability of a system without finding the roots of the denominator polynomial, that is, without determining the location of the poles for that particular system. So in today's lecture we shall talk about the Routh's stability criterion. The first condition of Routh's stability criterion is described by this statement. So if any of the coefficients of this denominator polynomial is negative or 0 in the presence of at least one positive coefficient, then the roots of this denominator polynomial will either have roots with positive real part, that the system will be unstable, or the roots will lie on the imaginary axis, that is, the system will be marginally stable. For example, if you have this denominator polynomial, so here you have a fourth order polynomial. There is one coefficient which is negative in the presence of some positive coefficients. So without computation of the roots of this denominator polynomial, you can quickly say that this system is unstable. However, if this condition is not satisfied, that is, all the coefficients are either positive or all the coefficients are negative, then we have to proceed for the next step, which is construction of the Routh's table. In the construction of the Routh's table, let's take some example and then demonstrate the construction of this Routh's table. So we start with the fourth order polynomial or denominator polynomial, that is a4 s power 4. We have this system with some numerator polynomial. Numerator polynomial does not affect the stability. This only determines the zeros. Stability is mainly determined by the denominator polynomial. So we have this denominator polynomial, and for this we start the construction of Routh's table. For the construction, we start with the highest power of s. So we have s power 4, and here in the first row we write the coefficients starting with the first coefficient and skip the second and write the third one, and so on. That is a4, a2 and a0. In the second row we write the coefficients which we have skipped, that is a3, a1. The coefficients here are determined from first two rows. The coefficient over here is obtained by multiplying this one with this and this with this one and dividing that with this coefficient, that is a3 multiplied by a2 minus a4 multiplied by a1 divided by a3. The coefficient over here is obtained by multiplying this with this one minus this multiplied by this. If there is nothing, then that is 0. So a3 multiplied by a0, a3 multiplied by a0 whole divided by a3. Then the entries over here are determined from these two rows. So let's, for the purpose of simplicity, give it some name. Let's call it B1. Then the entry over here is determined in the same way, that is b1 multiplied by a1, b1 a1 minus a3 multiplied by this entry, which is the same as a0 minus a3 a0 over b1. And then this entry is b1 multiplied by 0 minus a3 multiplied by 0, so that is 0 over here. This entry is computed from these two rows, this multiplied by this minus b1 multiplied by 0 whole divided by this term, which is a0. Once we have constructed this Routh table, then we look at the first column of this table and count the number of sign changes in this first column. The number of sign changes will be equal to number of poles of the system in the right half S-plane. To demonstrate it, let's take some particular example, and the example that we have is this system. We want to apply Routh's criterion to determine the stability of this system. There is no negative coefficient, so we have to move for the construction of this table. We start with the highest power of S, S2, S2, S1, S0. Here the entries first coefficient, and then skip the one, write the next one. Here the remaining coefficients, 10 multiplied by 10, 130. This coefficient is obtained by multiplying this with this one minus this with this one, so 310 minus 130 divided by 10. And here is this multiplied by this minus 10 multiplied by 0 whole divided by this one, that is equal to 130. This thing is equal to minus 72. So once we have constructed the Routh table, we look into the first column of this table and count the number of sign changes. This has positive sign, this has positive sign, this has negative sign. So one sign change, positive to negative, and then again from negative to positive. So there are two sign changes, which means that two poles or two roots of this denominator have positive real part, and therefore the system is unstable. Let's take one more example. We have a transfer function with the fifth order denominator polynomial, and we want to apply Routh's criterion to determine stability of this system. There is no negative coefficient over here, so we have to proceed for the construction of Routh's table. So we start with the highest power of S, S power 5. In the first row, we start with the first coefficient 1, skip the next one, write the next coefficient, skip this one, and write the next one. In the second row, we write the remaining coefficients, that is 2, 6, and 3. This entry is this multiplied by this minus this multiplied by this. So 2 3s are 6 minus 6 is 0, 0 divided by 2 is 0. And here we have 2 multiplied by 5 minus 10 minus 3 is 7, 7 by 2. Now next the entries in this row are computed from these two rows. So we proceed with that one. 0 multiplied by 6 is 0 minus 7, 0 minus 7 divided by 0. So something divided by 0 is infinity, and we cannot determine the sign of that infinity. So here we have some difficulty. So avoid that difficulty, what we do is replace this 0 with a very small number, let's call it epsilon. Once we replace it with epsilon, so then what do we get over here is 6 epsilon minus 7 divided by epsilon. So the objective of proceeding in this way is to get rid of this difficulty, that is something divided by 0, which is infinity, and we cannot determine the sign of infinity, and therefore we cannot count the number of sign changes. To avoid that difficulty, we have replaced this 0 with very small number. And now here this entry is so 3 multiplied by epsilon minus 2 multiplied by 0 divided by epsilon, that is 3. Next entry here is determined from these two rows. So this multiplied by this minus 3 multiplied by, now we can take this 0 because it will not create a difficulty. This multiplied by this one minus 3 multiplied by 0 whole divided by this one is, we get 7 by 2 over here, and then this entry is this multiplied by this minus this multiplied by 0 whole divided by 7 by 2, which is 3. So we have constructed the Routh table, and let's now count the number of sign changes in this first column. Here this is positive, this is positive number, and this is 6 multiplied by epsilon is very small number, minus 7 is, so this number has a negative sign, so one sign change over here, and from negative to positive another sign change. There are 2 sign changes, and therefore this system has 2 poles in the right half S-plane, and hence the system is unstable. Next we talk about another problem which arises in the construction of Routh table, that is if you get an entire row which is equal to 0. For that purpose we take this system. We have a 5th order transfer function, and now all of you know how to construct a Routh table for it. We start with the highest power as power 5. Write the coefficients starting from the first one, skip the next, and write it in alternate way. So here the first coefficient, the next coefficient here is 8. In the second row, the coefficients which we have omitted over here. Remember that in the construction of Routh table, if you multiply a row, entire row with non-negative constant, that does not alter the results. We multiply this row with 1 by 7 to get 1 over here, 6 and 8. This will simplify our job because larger numbers would be difficult to handle, and we get smaller numbers over here. So this entry, 1 multiplied by 6 minus 6 is 0, 0 divided by 1 is 0. So 1 multiplied by 8 minus 8, again we have 0 over here, and entire row is equal to 0. Here we cannot proceed for the construction of this table because we have an entire 0 row. To get rid of this difficulty, what we do is we construct a polynomial from a row above the 0 row, that is from this row we have this polynomial as power 4, the power, and then 6 plus 6s squared plus 8. Take the derivative of this polynomial, and 4s cubed plus 12s, and then we shall write the coefficients of this polynomial over here, that is we shall replace this 0 with 4, and then this 0 with 12. Now again we can multiply this row, this entire row, with some non-zero constant to get smaller numbers. So if I divide the row by 1 by 3, I get 1 over here and 3 over here. This will simplify our task. Here this row will now be constructed from these two rows. 6 minus 3 divided by 1 is 3, 8 minus 3 is 5, and then we continue in the same way. 3 minus 3 multiplied by 3 is 9, minus 5 is 4 by 3 over here, and 0 over here. Then what do we get for this 4 by 3 multiplied by 5 divided by 4 by 3 is 5. We have this, we have constructed the Routh table. Now we shall look for the sign changes in the first column, and there is no sign change in the first column. Therefore there is no root of this polynomial with positive real part, hence the system is stable. Another example to demonstrate the application of this Routh criterion. So we have this system and we want to determine its stability. Remember that whenever you want to determine stability or transient characteristics of a system, you always find the closed loop transfer function, that is the transfer function from input to the output. You remember the approach? The closed loop transfer function is the forward transfer function divided by 1 plus forward transfer function into the transfer function in feedback, that is the transfer function, closed loop transfer function. For this particular system, if we use this expression, we have this closed loop transfer function. You can verify it. That is given by and something in the numerator. We are not interested in that because the stability will be determined by the denominator polynomial. For this particular system, we want to determine the range of gain k for which the system will remain stable. For that purpose, again we construct the Routh table. Start with the highest power of s, s cube, s square, s1, s0. Write the coefficients over here, 1 and then 10, 6.5 and 10k. The entry over here is 6.5 multiplied by 10 is 65 minus 10k divided by 6.5, and here is 0. Then what do we get over here? This multiplied by this whole divided by this is 10k. We have this Routh table. For the system to remain stable, that is for this denominator to have all the roots with negative real part, there should be no sign change in the first column of this table. That is, if this is positive and this is positive, this must be positive, this must be positive. This line tells us that 10 plus k should be greater than 0, which implies that k should be greater than 0. From this row, what we conclude is this should be positive, that is 65 minus 10k, that must be greater than 0 for no sign change in the first column. That is 10k must be less than 65. If I bring 10k to this right hand side of this inequality, I get 10k less than 65, which implies that k should be less than 6.5. So this row tells us that k must be greater than 0, and this row tells us that k must be less than 6.5 for the system to remain stable. Collecting the information in both of these expressions, k should be between 6.5 and 0 for the closed loop system to remain stable. So although this Routh criterion does not tell us anything about the location of the poles of the system, it only tells how many poles will be in the right half S-plane. Otherwise, exact location cannot be determined by application of Routh criterion. However, we can utilize our intuitive knowledge and combine with the Routh table to determine some information, to know about some information about the location of poles. For that purpose, we take one example. Here we have a closed loop transfer function. Here we have an 8th order polynomial. Now you know the procedure to construct the Routh table. That is easy. We start with the highest power, s power 8. This row is now constructed from these two rows, that is 12 minus 22 divided by 1 is minus 10, and here 39 minus 59 is minus 20, 48 minus 38 is 10, and 20 over here. You remember that we can divide an entire row by some non-negative constant. So here, dividing this row by by 10, we get minus 1 over here, minus 2, 1, and 2. The only reason to make this division is to get smaller numbers, which will be easy to handle. If we proceed for the construction of next row, we have 20, 60, and 40. 20, 60, and 40. You remember the procedure. This will be minus 22 minus 2 is 20 divided by minus 1. So here. Now we can divide this entire row by 20 to get 1, 3, and 2. Next, what we do is construct the next row, 3 and 2. Minus 2 plus 3 is 1, so on. And then this row from these two rows is 0, 3 minus 3 is 0, 2 minus 2 is 0. Now entire row is 0, and we have learned the strategy to handle this situation. What we do is we construct a polynomial from this row, take its derivative, that is s power 4 plus 3s squared plus 2, take its derivative, which is 4s cubed plus 6s, and then replace the coefficients, these 0 coefficients, with the coefficients of that polynomial, which is 4 and 6. If you wish, you can divide this row by 2 to get smaller numbers, so that these are easier to handle. Next, we get 6 minus 3 is 3, 3 divided by 2, 3 divided by 2, and then 4 by 2 is 2. Here we get this multiplied by this minus 4, so we have 1 by 3 over here and 0 over here, and then finally 2 over here.